So in this video, we're going to go through and summarise a basics of vector calculus, so that way you guys over the holidays don't feel overwhelmed. It's a short topic. In general, some of the questions can be fairly straightforward, except there can be some really tricky exam 2 questions. So if you feel overwhelmed and can't do some exam 2 questions, or don't even have time to over the holidays, that is fine, but I do want you to try the coursework, and I'm going to try my best to summarise in a lesson what that coursework's all about. Now, first of all, if I turn to the third page, it says here that where vector calculus describes the motion of particles. And the motion of those particles, we could think about two dimensions, x, I and a j component, or we can think of 3 dimensions, and we'll see examples of those. Now, so generally speaking though, let's just say if I had a vector as a position of time. So what we can say is here that my I component is changing with respect to time, and we'll call that x. So whatever that component, that I component is, we're going to call x. Whatever the j component is, we're going to call y. And that is going to change with respect to time, of which we can actually have, I guess, parametric forms of equations. That's what the stuff we did in chapter 1. Now, for example, it's given an example here, but I'm just going to get you guys to turn to the next page and let's have a look at some Cartesian equations for a path. Now remember we're talking about, we've got a Cartesian equation. What's the parameter in both of these? We've got r of t is equal to natural log of 2t I plus 4t minus 1j. So what's the parameter in this time? Now, it could be theta, but generally speaking, we're going to say that for most vector calculus, we're talking about time. Okay? In the past, in chapter 1, parameter could be theta. So now what I'm going to do is we're just going to go through and do some of these. So for example, what we're going to do is we're going to say that that x is equal to log to the base, or I'm going to say log e of 2t. And what I'm going to do is I'm going to get t as a function of everything else. So therefore what I'm going to do is I'm going to take e to the both sides, and that means that I'm going to say that e to the x is equal to 2t, and I'm going to therefore say that t is equal to e to the x over 2. Now I can then say that if t is equal to e to the x over 2, therefore I've got an equation y which is equal to 4t minus 1. And therefore, I've got my expression for t, so I'm just going to put that in, 4 to the e to the x over 2 minus 1. So therefore, I now have my Cartesian equation, Cartesian, y and x. Okay, so we've now found a Cartesian equation. Now, the same thing goes for the second one. Now, I might skip the second one. You could probably sort of see that y is going to relate to x in some way. They're very similar. It might be a line. So in this first one over here, the path of the particle, we could actually say that that is 2 to the e to the x minus 1. The path of the particle is going to look something like this. Okay? So that's going to be the path of my particle. With this one, well, I won't do that one. We won't do them all. But what I will do is this one. First of all, we can say that x is equal to this part here, the I component. So x is equal to 2 cos of 3t minus 1. Now, and we can say that y is equal to sine of 3t. So if I wanted to sketch, so really, essentially, 12a is looking at these Cartesian equations, all right, and sketching them, which we've already done in chapter 1, more or less. Now, what I'm going to do is I'm going to say that x plus 1 over 2 is equal to cos of 3t. We need to find a relationship between those, and I'm going to say that y is equal to sine of 3t. Now, what would be my Cartesian relationship between these? I have cos and I have... So it's not going to work out like it did in the first one. What could you say that my Cartesian equation is, the relationship? It's going to be an ellipse. Yep, so I'm going to square... So therefore what I'm going to say is that cos squared 3t plus sine squared 3t is equal to 1. So therefore we can say that x plus 1 over 4, that's squared, over 4, plus y squared is equal to 1. So that's going to be... So therefore that's my Cartesian equation. Now you guys have been given solutions as well. The answers to all these questions throughout are in the back. All right, so I hope that's pretty much what you're going to have to do in your first part of the vector calculus, is sketching paths. But in order to do that, you need to use the parameter and a relationship between those parameters for x and y, and then find a Cartesian equation. Pretty simple stuff, I would think. Then we're looking at distance. Now, the distance of something is actually the magnitude. We're using this fact here that I've got some vector. Now this here is a position vector, but in actual fact that vector r of t, that position is r of t. Now if we want to find distance, that's actually, we're looking at the magnitude of something. We're looking at the magnitude of the position. So in this case, what happens if I was working out, it's given us this hint that the magnitude of r, which is the distance, is equal to the square root of r dotted with itself. Remember the dot product? What if I'm dotting something with itself, then we know that I dotted with I is 1, and 2t squared dotted with 2t squared is 4t to the power of 4, but we're told that at t equals 1. So what's the dot product of r dotted with r? Well, that's going to be 4t squared, where t is already 1, that's 4, plus log 10 of 10 of t. Now, t's already 1, so it's log 10 of 10 is 1. So that's going to be 1 dotted with 1, which is just 1. So therefore the distance there is root 5. Now...
So when it says like log, just like that,
yeah, log 10... Now, so what that's saying is log 10 of 10t, but t is 1. So that's log 10 of 10i dotted with log 10 of 10... j, dotted with log 10 of 10j. So log 10 of 10 is 1. So that's basically what is the dot product of j dotted with j. Well, that is 1.
But when you're not given the baseline, would you assume 10?
Well, you won't ever, yeah. In this case, to be perfectly honest, I don't even like that example.
Yeah.
I've never even seen anything like that perfectly. But we will basically, what we're trying to say is the magnitude of the speed. If I get r dash of t, what would be the magnitude of the velocity as a vector? What would that be? What would that be? Well, velocity is a vector, but the magnitude of that velocity is going to be the speed, isn't it? Okay, so all this was basically saying is that the magnitude of my, the distance r is equal to the magnitude of r. Okay, so that is going to be the distance. That's all that was saying. So if I then go ahead and look at this next part, you can see here it says here that if I have the position vector and there's a little dot, we could use a dot or a dash, it doesn't really matter, but you're going to see both, all right? And what we're going to then say is that r dot magnitude is the speed, which is just using the sort of thing we discussed there, using Pythagorean theorem, more or less, because the speed is a scalar quantity. So if you've got an expression as a vector, then the speed, the instantaneous speed, is the magnitude of that vector at that time. Of course, though, r dot of t, now there is a little dot there, okay, there is a dot on top of that r, that represents the velocity, okay, and remember, it's a vector. And what we're doing is we're deriving the x, or we're deriving the I component with respect to t, in other words, that I component being x, and we're also deriving the y component with respect to t, and that's being the y, okay? This stuff is stuff that we've really already considered. The same thing, r double dot of t is considered the acceleration vector. So we derive the position, the velocity again with respect to t, and that's going to give us the acceleration. So if I was to have a look and try this question here, then we should be able to find this fairly straightforward. An object has a position vector r of t, so we've got position with respect to time, of I, j component. Generally speaking, you guys will have a lot of two-dimensional questions, but some of the trickier ones can be like find the angle that a javelin hits the ground, and it's actually, we're given a vector in 3 dimensions, an I, j and a k component. And you might need to find an angle. Some of those questions can be actually really quite challenging. So I'm not going to say that this stuff's easy, but getting the fundamentals is fairly straightforward. So for this one, find the velocity vector v of t. Well, v of t we could call that r dot of t, or r dash of t, or as we have just stated, v of t. Now remember that they are vectors, okay? So I want you to start using vector notation, which is something a lot of us didn't do very well in the application task. Now, we're deriving that with respect to time, so therefore we can say that the velocity as a function of time as a vector is equal to, just deriving that, 6t minus pi cos of pi t I plus, and I'm deriving that minus t, so the derivative of minus t is minus 1. So we've got minus e to the minus t plus 2j. So that is my velocity vector in terms of time, which is going to change in terms of time. So now remember that if I go to the end of this document, and what was that question? There you go. So we're deriving the position vector with respect to time, and we've got our I and j components there. So you've got your answers throughout the way. My advice is to work through as much of this as you can. All right, and then, but given today, I think you'll sort of realise that this topic is pretty straightforward, particularly given what we've just been through. Now it says find the velocity of the object at t equals 2. So what are we doing? We're saying r dotted at 2, if you like. Or we could say that v of 2. These are all equal statements, as just depending on the context of the question and what's been provided. So we're subbing in, we can work out that the velocity, which is a vector, at 2. So I'm subbing in 2 for t, which is going to be 12 minus, now cos of 2 pi. Cos of 2 pi is 0. And then therefore, what's that? Cos of 2 pi is the same as cos of 0, which is 1. So that's going to be minus pi I. Then subbing in 2 there, that's going to be plus minus e to the minus 2 plus 2j. Now, it's asking for the velocity. That is the velocity as a vector. The velocity of a vector, now that I is obviously just not, is just some constant, if you like, 12 minus pi. So it's going to be roughly around about 8.86 I. And then, of course, we've got some, well, that's going to be a positive value, that's going to be negative, that's going to be small. And then we've got roughly 1.5j plus 1.5j. So that's our vector component. So in other words, that we could sort of say that, let's just say that that was approximately 9i plus 3 over 2j. Let's just say if it was that. That means that we could say that at that instant, that vector could be basically sort of saying that we've got more component there, less component there. We could sort of be saying that speed is in, at that point, is in that direction, for example. All right, that's pretty much all it's saying. And it has a magnitude. We can find the magnitude because it says find the average velocity in the first 2 seconds. Well, that's a little bit different. In the first 2 seconds, the average velocity, isn't the average velocity just going to be more or less rise over run, if you like? Okay, so therefore the average velocity. So why don't we work out what r dot of 0 is? When time equals 0, what's going to be the velocity at 0? Well, we're going to have subbing in t equals 0, so that's going to be minus pi I plus j. Okay, and then just one second. So getting back to that, we don't need this. We actually just want the position. So the average velocity is the change in position sort of over time, if you like. Now, we can then work out, so the position, where is the position at t equals 0? So you guys could work out that at t equals 0. Now, I'm not going to do this because I want to get through as much of it as I can. But when we get to question 3, okay, what they're saying is that the position at 2, subtract the position at 0. I didn't read the question. Sometimes I'm going to do this. I do this a lot lately. And then I'm dividing by 2 seconds. And you can see there that the average velocity is still a vector, of course. Not the average speed. Remember, if you asked average speed, speed's going to be a scalar quantity. Okay, so that is pretty much just the average velocity is equal to more or less displacement over time. And we're going to have to work out the position at 2, the position at 0, and that's how we do it. All right, getting back to where we were. Another question here on a helicopter. If it says find the vectors describing the helicopter's initial position, velocity, and acceleration. So what would we have to do here? I've given its position, so therefore I derive to get the velocity with respect to t, and then I derive again to get the acceleration. Now, we're eventually going to look at, and I'll definitely cover it in term 2, some questions where we go the other way. But when we go the other way, we have that, rather than have that constant of integration, we've actually got a vector, which is c, is rather than be a constant, it's actually a vector. So that can be one of the more trickier things. We also have to look at cosine of the angles, and we're looking at vector things, but you guys have already done that. But let's have a look at this one. The position of an object, r meters, is given by this. Find the speed at time t seconds. So how would we do this one? So question 5. Well, first of all, we have a position vector, So we need to work out what that velocity vector is. So I'll just call it r dot of t is equal to, deriving that is going to be 6 cos of 2t I minus 6 sine of 2t j. So I've derived it, and it says find the speed at any time in seconds. So the speed is the magnitude of that velocity, which is the magnitude of the x component and the y component. So in other words, I'm going to take out 6 and I'm going to square that, and then I'm going to take out cos 2t squared plus, if you like, minus sine of 2t squared. As it turns out, that's going to be a positive result, but what we've got is going to be that is 36, and cos 2t squared plus sine 2t squared is 1. So therefore it's going to be, find the speed at time t seconds. That is going to be 6 meters per second, isn't it? Yeah? Now if I go to let's check the answers. Yes, 6 meters per second. All right, so speed. We need to know the difference between our vector and be careful to read the questions. Okay, because speed and velocity are two different things. Now, I'm going to just let that and more or less say that I'm going to move on to the next part, or at least try to give you a bit of an overview of the next part. I'm pretty confident that you could do these questions no problems. The next thing is, this is the thing that was going to be the trickiest part, is that anti-differentiation of the acceleration is a vector. So, over here, notice that if I zoom in, that constant of integration is actually a vector. So we need to be given, for example, if I'm anti-deriving the velocity vector to position, then I might need to be given some initial conditions, such as you are starting at the origin, and the origin would be x equals 0, y equals 0. That is going there, that's your initial position, for example. So that way we can actually solve these problems. The anti-differentiation of the velocity vector will give you the position vector. All right, so it's pretty intuitive. Now, it says here, it's got an example, so you can work your way through that. But let's have a look at just what we've got here. Now, it says here the acceleration of an object is this thing here, which is just with respect to I. Now, bearing in mind, though, let's have a look at this initial condition for the velocity. For the velocity does have a j component. Okay, so what that's saying is that the velocity when time is equal to 0 is 2i minus 3j. There's an I and a j component. So it's saying here, find an expression for the velocity. So I'll get my little highlighter, I'll get rid of that, and let's have a look at that. So what we can say is that the velocity is equal to the antiderivative of the acceleration, which is 2 minus et, I, and then we've got some plus c, which is this constant of integration, but it's not a constant, it's a vector. So, now, remember that there's also, what are we anti-deriving that with respect to? T. So there's a t that goes there. Now, what we're doing then is, what do we do to the power? We have to have a look, we have to divide by the derivative. So that's going to be minus 2 e to the minus t plus this constant here, which is a vector. Now, it says here, v of 0 is equal to 2i minus 3j. So we now need to find what that vector is. 2i minus 3j. Notice that I'm using vector notation. When t equals 0, that means that e to the power of 0 is going to be 1. So that's going to be minus 2 plus c. Now, what we can say, therefore, is that c is equal to 2i minus 3j plus... Now, just quickly... Yes, just one sec. This is minus 2. What's this? It's an I. That's right. So therefore, we're adding 2i to both sides, aren't we? So that's going to be 4i plus 4i minus 3j. Okay? Now, we've found our c, so therefore we can say that our velocity with respect to time is equal to, minus 2e to the minus t I plus 4i minus 3j. Now, you wouldn't write it like that though. What you would do is you combine the I components together. So what I would say is this, minus 2e to the minus t plus 4i minus 3j. And that is my expression for the velocity. So that's... now, once again, you can see here that we're then asking for a position. So it means that we have to do it again, don't we? And when we do it again, we have to use this initial position to find our other constant. Now, by the way, I've used C here. Would I use C here again? No. Use D or something like that.
So does the I just act as like a random coefficient for the gravity? Or do you just like...
Just one sec. Of course, here we can say that R of t is equal to the antiderivative of, with respect to t, of the I component and the j component. So I'm just going to do that straight away. So dividing by negative 1 here is going to give me 2e to the minus t plus 4ti minus 3tj plus a constant of integration d. Now, which is a vector. So now what we can say is that r of 0 is equal to 8i minus 2j. So therefore we can say that 8i minus 2j is equal to all of this to the power of 0, which is equal to 2i, zeros there, minus plus 0j, subbing in t equals 0, plus d. So therefore d is equal to, subtract 2i from both sides, d is equal to 6i minus 2j. So now I then just get that 6i minus 2j, and that goes there. And there's our expression. So if I was to go to 9b, oops, we're going to have that expression there where they've collected the I component and the j component. And remember that that d value goes in there. It was 6i minus 2j was what we found to be d. So you can see there that it's there. All right, now I know that that's a lot to cover in a lesson. I'm just going to give you some other general pointers so you're going to find your life a little bit easier. First of all, remember that I've emailed you the solutions to Chapter 12, and they're also on Ivanhoe Connect. That's the second thing. The next thing is that pretty much, yep, so we've got those acceleration questions. The next thing is the applications of vector calculus. Now, that's the theory. Then we've got to apply it. We, for example, can have a look at some of the things such as collisions. Two particles can be in the same position at different points in time. Okay, for example, we could have a circle as a Cartesian equation, or we could have various things. Just because the position is the same does not mean we've proven that they collide. Two particles need to be at the same position at the same time in order for a collision to occur. And so these are some of the things that we're looking at. We're also going to be looking at distance between points, which is obviously, we did an example there. We're looking at the speed. We could be looking at the instantaneous velocity. The instantaneous velocity is a vector. Okay, now, so these are some of the things there. There's some applications, okay, and those applications I'll get you. If you're struggling a bit with some of those, don't worry, when we get back, I will go through a lot of the application questions early, so that way your test in the first week, which will have some applications to it, you guys are going to be feeling okay. Are there any questions about this so far? Would you say that it's pretty easy topic? Doable? Very doable? All right, well, look, I must say, if you're overwhelmed, that's okay. You're going to have to then work your way through all the things I've given you over the holidays and try your best to get the coursework done for the chapter and do these practice tests that I've given you. I'm going to stop that video.